Good morning, everybody. Today is a Codeforces round, round 672. It's a Div2 round, and I'll be competing live. And then at the end of the video, I'll have my solutions. So it looks like I forgot to register yet again. Should have done that yesterday, but oh well. It's a Div2, so it's not a big deal. It's mostly going to be me solving them and having fun. But let's see. Okay, so this person decided to try to make a test chamber, but there is one detail. What? Okay. He needs n cubes. The ith cube has volume ai. He wants to place the cubes in such a way that they're sorted by volume. To achieve the goal, he can exchange two neighboring cubes. He's impatient. If he needs... So this is just like every pair, right? So basically, is it sorting in decreasing order? Yeah. So we can just read in the array. And then if a at I is less than a at I plus 1, less than or equal to even, then we don't need to swap them. So this out, yes, and then continue outer. Otherwise, sys out, no. So that should be good. Oh, yeah. All right, so that's cool. Since oh man, what's going on here? If a at I is less than or equal to that. So, this should be fine. Then I'll submit this as soon as I can register. So since I forgot to register for the contest until 10 minutes in, I have to just sit here and wait, but that's fine. Let's read problem B in the meantime. We urgently need rock and lever. What? I don't even... Is there like a theme for this round or something? I don't get it. You're given a positive integer n and an array of a positive integers. The task is to calculate the number of pairs where a and I is greater than or equal to a XOR I. Well, the and will never be... Oh, it might be greater than. It's a good question. I don't know how to do it immediately. Let's draw out what it means to and into XOR and see if it's like super obvious once we have that. So you have 1 0 1 0 and 1 1 0 0. You and them, then you get 0 0 0 1. If you XOR them, then you get 0 1 1 0. All right, so what numbers are we trying to find this for? Where the and is bigger than or equal to the XOR. So that means the first bit needs to be something they both have for that to be the case. The first bit either has, they both have. After that, it doesn't matter. So if we know what this first bit is, like let's say we know what this is, then all of these are free. This is just like 2 to the n. So it's easy to calculate. Then we can brute force what this first bit is. Yeah. So this should be pretty easy to solve, I think. Wait, what is this? hang on. Oh, we have to pick 2 integers in the array. Got it. Sure. So for each integer in the array, we just need to store what the biggest 1 bit is. And then it's like n choose 2 for those. So you can choose 4 and 3, and that's it here. Because this is, oh wait, no, 4 and 7. This is 1, this is 2, these are both 4, and this is 8. Yeah. Okay. So let's code that real quick. So now hash map integer to integer. So for each integer in the array, I equals integer dot highest 1 bit of I, so we don't care about everything else. We need our answer, which we'll print out at the end, and then ans plus equals map dot get I, get our default, and then map dot put I, map dot get or default I 0 by default plus 1. That should be good. All right, sounds good. Can we submit yet? No, 2 more minutes. Well, we'll read C. We'll read C2 because I think I'll be able to solve both, and then we'll go from there. All right, interesting. The easy version has no swap operations. Okay. Pikachu is a cute and friendly Pokemon living in the wild Pikachu herd. It has become known recently that the infamous Team Rocket wants to steal all these Pokemon. Pokemon trainer Andrew decided to help Pikachu build a Pokemon army to resist. Andrew counted all the Pokemon. There are exactly N Pikachu. Strength of the ith Pikachu is equal to AI. All of these numbers are distinct. You can choose some subsequence of Pokemon. So you can choose you can like delete a bunch of Pokemon. Okay, now the strength of the army is equal to the alternating sum of elements. Yeah, okay. What is K? Can K be anything we want? Can't search for K. It looks like they don't give bounds on it, so I think K can just be anything. So I don't think K is really... Yeah, K can be anything, I think. So... basically, the array looks like this. So you've got like some elements. As you increase the index, they vary like this maybe. And you're concerned about this total distance here, I think. Why would you not pick everything though? That doesn't make sense. Oh wait, it's not the absolute value of the difference. Okay, so it's positive this. Yeah, okay. Oh, that is the case though. Yeah, so it would be, it's this value here, because you add this, then subtract this. Then you add this and subtract this. So you get this. And then you add this. Maybe a better way of looking at it would be, or an easier to implement way would be, you get this for free, and every time there's an increase, you get that for free. What are the other types of operations? Well, all right, let's submit. So does C just not have any operations for C1? Oh, Q equals 0, okay, yeah. So we got both of those. Well, I guess C1 is pretty easy, right? Let's just code up this picture, and then we can handle C2 in a minute. So okay, so then long int equals 0, well int equals 8i, 8 0, then for int I equals 1, I less than n, I plus plus, int plus equals math.max is 0, and 8i minus 8i minus 1. So the answer. Okay, well, we might as well just submit this, and then we can move on to C2. But I've lost points before for waiting to submit the easy version when it takes like 5 seconds to code. So let's just make sure. This also is nice because it verifies that like the approach is somewhat correct. Yeah. Okay, approach is right. So now we just need to maintain this. So we just need to find a way to maintain this, which shouldn't be too bad. Okay, how do we do this? So So int array a equals new int array n. Now we'll change I to the next int, pass in the array. Start the answer at 0. Change all these things. Now we have a bunch of queries. So we'll have, we want to swap two integers. Is that how it works? Yeah, okay. Can they be the same? They can be the same. Okay, so we print q plus 1. Okay, so we'll need a print writer. Okay, now for each of these queries, we need to be a little bit smart about it. So, well, yeah, okay, int from equals this, 2 equals this, if from is not equal to 2. I mean, it should be fine even if they are equal, to be honest. Yeah, so int from val would be 8 from. Well, I guess just int temp equals 8 from. Then change from to 8.2. And change 2 to the temporary variable. And print the answer. Okay, so now we just have to implement this change method. So what happens? So if, let's say, yeah, so ans minus equals 80, then plus equals 80 at the end. So now we handle that, so we just have to say a at end equals new val here. Now we just have to handle the increasing part. So if ants, or if end is greater than 0, then ants minus equals math.max of 0, a at end minus a at end minus 1. And then we want to add it back in. So those are the two halves this is part of. Okay. That should handle all of it. Good. I think that's fine. Three, 4, oh no, I'm wrong. Okay. 3, 4, 2, 2, 2, 9, 10, 10, 10, 9, 11. Looks good. I think that's, I mean, it was like a very easy problem for sure, but I think it's a good problem for a Div2 because it's like an introduction to maintenance sort of problems. So if you're like new to maintenance stuff, that would be a good way of learning it, I think, from that problem. So it's definitely a good problem to upsolve because it teaches that skill. Well, we'll listen for the result. How about that? All right. These people have overcome many difficult challenges. We're probably doing pretty alright then, right? I'd imagine. Not bad, not bad. Yeah, okay, let's solve D then. He's surprised, but Sane gave an explanation quickly. Okay. There are N lamps with the spirit tree's light. He knows the time of turning on and off the ith lamp. So it turns on at some time, turns off at some other time. To open the door, you have to choose K lamps in such a way that there will be at least one moment in time in which they are all turned on. He decides which of the K lamps to pick. He's interested. How many ways are there to pick K lamps such that the door will open? Okay. Interesting question. So, in other words, you've got a bunch of ranges. How many sets of K of those will be intersecting? So we're going to want to do a sweep from left to right probably. And to avoid overcounting, we can say we know that the thing that that ends here is part of it. So we know this is part of it. Then we need to choose K more out of whichever ones are available here. Or I guess whatever ones are available except for us. So if this is like, let's say this is the range here. So we can choose, we have 3, choose 2, if you want like K equals 3 maybe. Then maybe we could end here. Yeah, okay. If we end here, then we have 3, choose 2 again, because there are 4 things and we need 3 others. Then if you end here, you have 3, choose 1. So I think that's right. Okay. So we'll have an L and an R, public seg from int L to int R. Oh wait, these aren't actually comparable because we're not sorting these. So we just want to sort some events though. So we'll have a static class event. So it might be a start, and then it also needs some segment. It also needs a time. Oh wait, so we can just do that. So int like x will be, if this is a start, return s.l. Otherwise, return s.r. So that'll get the start of the segment or the end of the segment, depending on whether this is a start or at the end. So if x is not equal to o.x, then return integer.compare those two. Otherwise, if the x's are equal, then we want to check which ones start first. So if start is equal to o.start, then return 0. Otherwise, you probably want to start before you end, because that way our sweep will work correctly. So if start, return -1, otherwise return 1. Okay, so very good. So now, is it a single test case or multi-test case? Single. We'll read in n is the number of ranges, and then k. Okay, so int n equals this, k equals this. We have this many segments. We also need to keep track of the mod. Then we'll need static void add into a into b, return a plus b mod plus mod mod. Static void multiply. These should probably be longs everywhere. A1b return a times b mod mod plus the mod static void exp long base long b 0 return 1. This will take some number to some power. Otherwise return multiply half by the base, which we can use to get the mod inverse. Okay, so now we just need our factorials. We'll pre-compute those. Facts equals new long array. Let's just do 10 to the 6. Facts at 0 equals 1. Form equals 1 is less than facts dot length. Then for each of these things, facts at I equals facts at I minus 1 times I. Under mod, of course. And then we'll calculate the rest of it when we'll calculate factorial inverses when we need them. So now we just need n choose k. So if we have some long n, some long k, return, so it's n factorial times, or divided by n minus k factorial. It's not static, it is static. What's wrong with this? Oh, these need to be ints. Divided by k factorial divided by n minus k factorial. All right, very good. So now we just need all of our events. N times 2. So for each event, events at 2 times n, there's new event. From segs at I, this one can start, and then we also need the same thing, but ending. Yeah, okay. 2n plus 1. Now arrays got sort this. Now we need to process all of these. So int n segs equals 0. This is how many were, like, I guess this will be our current counter. So this is the counter of how many segs we're in. That'll be 0. Then for event E and events, we also need some long answer equals 0, which we print at the end. All right, so now for each of these events, if e.start, then counter plus plus. Otherwise, if it ends, then counter minus minus. Now we have some things we might need to choose from the rest of them. So what if n is 1? K can be 1. Well, 0 choose 0 is 1, so that's fine. Okay, so now if counter plus 1 is less than k, then we can't pick them, so then just continue. Otherwise, we can pick some subset of the other things that are still alive to use. So in this case, ants equals add the ants, and n choose k. We want to add, how many things are there to pick from? Well, there are a counter of them. Then we want to pick k minus 1. I think that should be fine. We're not pre-comping. Very generous on the test cases here. Looks good. Any runtime concerns? I don't think so. Should be good. So let's just submit that. All right. Yeah, I kind of saw that one right away. So that was one thing that made it easy, I guess. All right, I think we're good there. Let's read E. Is this the last problem of the set? Yeah. E. Okay. Lighthouse Keeper Peter commands an army of N battle lemmings. He ordered his army to stand in a line and number the lemmings 1 to N. Some lemmings hold shields. Each lemming... Really? They're gonna be like that? Alright, fine. We can fix that. Fact inverses. So it's just this n choose k needs to speed up a bit. We could probably just remove these mods and do it too. Yeah, we're not subtracting anywhere, so we can just go like this. That's like a ×2 speed up because the mod was a slow part. Then on top of that, we can make it even faster. Okay, now fact inverses at fact length minus 1 equals mod inverse of facts at facts.length minus 1, warrant I equals facts.length minus 2, I is greater than or equal to 0, minus minus, and fact inverses at I equals fact inverses at I plus 1 multiplied with facts that, or multiplied by I plus 1. Okay, now these should just be fact inverses. And then I think we should be good. Let's rerun some of the samples though. I guess we'll just rerun all of them just to be sure. Okay, well. Yeah, that was a combination of not like wanting to code it quickly and also like not being in C++. So, like I didn't code the factorial inverses part because I thought I could save time, but I didn't really need to. This should be plenty fast, I think, because I've just removed like a log factor on the solution. Alright, last problem. So, Lighthouse Keeper Peter has an army of N battle lemmings. Yeah, sum of shields, blah, blah, blah. The more protected his army is, the better. To calculate the protection of an army, he finds the number of protected pairs of lemmings such that wait, what? He finds the number of protected pairs of lemmings. That is, such pairs that both lemmings in the pair don't hold a shield, but there is a lemming. Okay, wait, what? So a pair is protected if both lemmings don't hold a shield, but there is a lemming with a shield between them. Okay, I think I see. Now it's time to prepare a defense and increase the protection of the army. To do this, he can give orders. He chooses a lemming with a shield and gives him one of two orders. Give the shield to the left neighbor if it exists and doesn't have a shield. Give it to the right neighbor if it exists and doesn't have a shield. In 1 second, he can give exactly one order. It is not clear how much time Peter has before the defense, so he decides to determine the value of the maximum army protection K for each I up to and choose 2 if he can give no more than K orders. Or for each K. So my initial thoughts are it screams DP because of these tiny bounds. But maybe it's also like, I don't know, it also feels a little bit like flow heavy. Feels like flow on n squared maybe, because it's the kind of choice of like, you don't really know what you're going to do initially. So it's, I'd say either flow or DP probably. Yeah, so what does it optimally look like? Yeah, I guess let's look at this. Well, is it have all of them in the middle? Probably is have all of them in the middle. So the most, if there are 3, so we've got 2 shields, right? So the most one shield could possibly contribute would be splitting it in half like this. So the biggest the answer is ever going to be is when you have all the shields in the middle. Yeah, okay. So that's what we're ultimately going for. So now I guess let's look at this example. So we have 4 zeros, 4 ones. 0, 1, 1, 0. So in 2 steps, we can get 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0. This takes 2 turns. But then we would like to move everything over by 1. So we would like to go like this. Wait a minute, what? No, that's not true, because this is, so you don't want them all in the middle, because that double counts certain pairs. Yeah, so you don't actually want, if you want this, because now you have this pair, and this pair. Okay. So maybe I'll just like throw out some DP ideas, see what sticks, what's even possible. So we're gonna need the position, obviously. We've got a bunch of zeros, rather. Let's say the zeros are stationary and the ones move, because that's basically what happens. And then we have some ones in places. So we need the positions, we need the number of ones we're carrying. Or it's not the number of ones we're carrying, it's like which one we would consider placing next. So it's the number of positions and then like which one we're at. Which one we would place next. Then we also need to know how many zeros, like, yeah, we need to know how many zeros we have in the bank, basically. So if we had this one here and this one here, or maybe we don't. If we place a 1 here, got 1 here. If we place a 1 here, then we get all of these points for free. So we don't need to know that. We just need to know, okay, the last time we placed a 1. So which position we're at, which one we're considering placing, what the last position is, and then also the total number of moves, right? Yeah, total time. So this would be correct. The runtime here would be n times n times n times n squared. How big is that? Too big. But we can do 80 to the 4. Okay, so we need to optimize this somehow. So what is the DP state? We're doing which position we're at. Which one we're about to place. The last position. Okay, interesting. And this will equal the max return. We can maybe try a state inversion where we store the max returned instead of the total time, and the total time is like the result of the DP. The issue with that is that, like, we still have an n squared. So we're here. We know the last thing was placed here. We're considering placing this. Well, if instead of considering placing this, we consider placing the next position, that would remove this from our DP state. We get rid of this. Now we need to try all next positions. This total time acts in a kind of weird way though, because it's like decreasing and then increasing. Is that weird though? That might be predictable. Feels like this is a real spike in difficulty. Feels like every problem was super easy up till now. Yes, yeah, that's just reflected though. Okay. I'm gonna get some more water. It might be ternary searchable if we have a given line. It's also possible this is a divide and conquer DP. Yeah. Divide and conquer feels much better. Let's try divide and conquer. So we have our first line. We don't want to know where we place it. Now we're looking at this part here. So we need to know the left end of the range. Well, let's say we place something here, and maybe there's more stuff over here that we don't care about. So we need to know the left end of the range, the right end of the range. We need to know the first line. Like L1, and then the last line, L2 or whatever. and we brute force where we place it. So the state is end of the fourth. Then the transition is order size between these two. But which pairs of lines are there? Not that many. I think this feels more the way to go. It feels like this is much more promising. So yeah, so here's the idea. So we're gonna have we have a bunch of lines. Let's say we place one of them here. We know the cost of doing that. So we have like some like C1 for placing this. Now we have a bunch of lines here and a bunch of lines here. These two groups. So I guess what do we want to return? We want to return like an array of size n squared. Well, like, what does this array actually store? We want to store the minimum. Or we want to store the maximum value. Yeah, of maximum value for each cost. So if we have something here, we've got this array here. We also have this array here. How big are the costs? Costs are pretty big, but the values aren't. The values are the size squared. Well, they could both be size squared, really, I think. So the cost, this is n squared. So we've got some n squared array here, some n squared array here. We want to merge them by distributing the cost between C1 and then each of these arrays. So in order to merge, we can't use like anything special, I don't think, because we want the min of this, this, and this. Yeah, you can't do FFT for min. So how do we, so the merge costs n to the fourth. That's a problem. Because we have to do this like n different times for each split point for the C1. Wait, maybe it's not. Yeah, it is. It is n to the fourth. Because the array is size n squared, we, for each position, need to consider linear loop. Maybe divide and conquer isn't a good idea because we yeah, it's not obvious. Like you have to go down all these paths anyway. You can't like find the best path and then go down it. So maybe this is just not helpful. In this case, we need what? A min of all of these things? Yeah, let's just try this naive thing, but speeding it up fast. So we have dp at which one you want, where the last position was, and then the total cost. This is equal to the max value. And then the transition will be place the next one in all positions. So there's your last one. Maybe it came from here. So in this case, we would say like cost plus equals 1, 2, 3, 4, 5. How does our value change? The value changes in an odd way though. So I think we need to just incorporate like all of these places you could place it in. If you were to place it here, then your new DP state would look like this. Matters where you placed it from. Oops. How does this look on the scoreboard? Nicely done. So it's tricky, but it's not impossible. What if there were like some sort of way of doing this with flow, maybe? Feels like it doesn't fit very well. There would be some simplification I need to make. And I'm so close, but I'm just a factor of n too big, I think. I've got like an n to the 5th instead of n to the 4th. Which position we're at? Well, maybe we have small enough constant factors. Let's think about this for a minute. Which position, which 0 we're at, which one we placed last, and then how much cost do we have left? I guess this is like last one placed, really. So this is a divide by 2. This is a divide by 2. So it's n to the 5th over 4. Yeah, it's 8 seconds. It's not going to happen. right, so what is the inverted state? So we care about the position. Well, we care about a couple things. Let's say we want to calculate equals the min cost. So if we want to know the min cost, then we need to know the number of points that we need, or the number of pairs, I guess. Yeah, okay, so we could probably do this times log. So maybe end of the fifth with speed up is what's intended. Ugh. Or end of the fourth with the speed up transition. DP at last one position, then which one we're at, And then the cost left. This is equal to the max value of doing that. We want to add something here. That's tricky. I feel like this is not the right path to go down. But I don't know that I have any better ideas. Maybe let's do some examples. The first turn we want to do this, so then you have this here. Which is 3 times 3. So initially you've got 4 plus 5 equals 9. Now we have 10. Maybe we want to eventually get to this. It's 8 plus 8, which is 16. Wait, this isn't 10, this is So this is, yeah, this is 8 plus 5. Then this one is 9 plus 5. No, it's not 9 plus 5. This is 8 plus 1, so this is 9. Then this one is 9 plus 2. Eventually we would get to eight plus 8. So that's 8, or 8 plus 4. It's possible there are only a linear number of these values. I don't have a proof for it. In order for that number to be small, well, I guess there are lots of big numbers. There aren't that many small numbers, but there are a lot of big ones. I don't know. Wait, maybe the slow DP is actually fine. DP at position. Which position you're at, which is 0. Then which one. Then the last one placed. And then the cost left. So this is n squared divided by 2. The last one placed, this is n over 2 on average. Well, it's like the number of zeros over 2. Which one you're at is the number of ones. So really, we have like a divide by 2 here again. Divide by 2, divide by 2, and divide by 2. So it's like... It's like 80 to the 4th. 80 to the 5th, rather. Divide by 16. I wonder if this passes. I would hope not. It's kind of boring if it does. It is just max calls though, so it should be pretty fast. Yeah, I'm not sure. I'm not gonna code it because I don't know. I don't think it's super valuable to me, and also I have like real work stuff that I have to do after this. So yeah, let's go over solutions to all of the other problems, and then I'll talk about that solution idea. But I'm not sure if that's the intended runtime or not. So all right. So solutions. Oops. So problem A, cubes sorting. The problem is you have an array and you want to sort it. So maybe your array looks like 7, 3, 5, and then you want it sorted, so you want 3, 5, 7. What you can do is swap two adjacent elements, and you can do that as many times as you want in order to sort it. So that's always possible. One thing you could do is if you do bubble sort will always swap two adjacent elements, and the total number of swaps you do will be n choose 2 if you do bubble sort. So that's why bubble sort is n squared, but all of your swaps are between two adjacent elements. Now obviously bubble sort isn't a great sort, but there is an advantage to it, which is it's easy to think about certain problems like this one, because it makes it obvious like how it works and that some sorting methods are possible. So here we know it's possible to sort. We also know in this case we won't swap these two elements because the 3 is smaller than the 5, so they're in the right order. Since that's the case, we won't take all of our n choose 2 turns. It'll take less than that. So basically the only time it will take all n choose 2 turns is if the array is sorted in decreasing order. Yeah. So in this example right here, it's strictly decreasing. If there's ever any pair that we don't need to swap, then we could just use bubble sort to sort it in, at most, this many moves. So yeah, that's the idea for problem A. So just check if it is sorted in decreasing order. If it is, then the answer is no, otherwise the answer is yes. All right, problem B, rock and lever. What was the idea behind this one? Oh yeah. So let's look at when we AND two numbers and OR them. So like I'll draw this number here and then this number here. Kind of gives a good example of what happens when you AND and OR them. So when you AND two numbers, the only time the result will be 1 is if they're both 1. When you XOR two numbers, you have all of the same two numbers. Then the result is 1 if they're different. So here this is a 1, that's also a 1, that's a 0. Now, if we're comparing two numbers in binary, all we care about is the first instance in which the two numbers are different, right? So we care about if these two things are the same, we can ignore it. So like we can ignore this position here, because if the two numbers we pick at a given position both have zeros, then the XOR and the AND will both be the same. But now for all of these other positions, they're different. So these are the important ones. We want the AND to be bigger than the XOR. So we want this thing to be a 1, where it's a 1 for the AND and a 0 for the XOR. That's what we're trying to find. Which means there's only one way of doing it, which is this here. So we need the first time that you don't have a 0 in both positions of both numbers, or in the position for both numbers, there has to be a 1 in both positions. In other words, the highest 1 bit of those two numbers has to match. So as an example, if we do 5 in binary, looks like that. And then let's do 7 in binary, looks like this. We can tell 5 and 7. Well, that's equal to 5. And then 5 XOR 7 will be equal to 2. So we want this 5 is bigger than 2, so that's good. So that's really all that matters. So to implement that, it's pretty easy. All you need to do is check the highest 1 bit, and then you count how many pairs there are for that highest 1 bit. So you can match this I, like I just care about the highest 1 bit of I. Everything that has that highest 1 bit in the past, I can match this number with. Otherwise, and then in the future, something can match with me. So that's it. It's like super easy to code. All right, so then on to problem C. The idea behind problem C is there's like a interesting way of looking at it that I think is pretty helpful. First of all, what's the problem statement? So we're gonna pick some Pikachus or some Pokemon. Yeah, they're all Pikachu. So we're gonna pick some Pikachus, and they have different powers. And I'm gonna draw this as like a graph. So on one axis, this will have like the index in the array, and this will be the power. So we'll have a bunch of different Pikachus. Maybe they look like this. We've got some variation here. And we could pick some of them. If we pick this one, this one, this one, and this one, for instance, then we get some points for all these. So we get positive this, positive this, and negative this. Obviously, it would be better to just not pick this last one, right? If we can just do this, then we get the same score, but it's strictly better. So we're always going to want to start with a positive and end with a positive, since all the powers are positive. We can also kind of imagine this in a slightly different way. Let's imagine this, we like kind of both pick and don't at the same time. So we can imagine we get it, but then we also delete it, right? If we think about it like that, what that gives us is we get this bonus right here, then we also get this bonus here and this bonus here. So every time there's an increase in the array, we get all of those values. And that's an equivalent way of saying what the maximum score is. If you imagine inserting a 0 into the beginning of the array, then it's just all of the increases. So we want to maintain this throughout all of the queries. It's really easy to calculate this. For C1, you just have to calculate this value. So for C1, all you do is just like add the first value of the array, and then every time you have an increase, you add the value of that increase. That's your answer. For C2, you have to be a little careful So what might happen is, like, what I did is instead of having like swap two Pikachus, I had changed the power of a Pikachu. So this one, instead of being this, I'm like, okay, now move it to this position here. You have to kind of handle that, like, you have to be a little careful with how you handle that. So there are a couple possibilities. If this is the thing you're going to move, if it came from something and this used to be an increase, first you have to subtract out that increase. And then after it moves somewhere else, maybe it moves to like here, then you have to add this increase back in. Maybe it also might move to below this, in which case the increase you add in is 0. So you have to do this from the thing that you move to the one before and also the one after. You have to be kind of careful with that. Yeah, I think that's it. That's like the idea behind the solution. And if you can just maintain that, and that will give you the right answer. So I guess maybe the last part that I should mention is, why can we do this? Well, we could keep this if we wanted to. We could also keep this if we wanted to, but if we wanted, like, if we didn't want either of those, we could just skip this entirely and go like that. And that'll give us the benefit that we're calculating here. So yeah, I think that should be clear. For code, I'll show you C1. C1's super easy. It's just this right here. But C2 is a little bit more messy. Initially, I start with an array of all zeros, and then n times I just call this change method. Because since I already have the change method written, then it makes it easier to handle. So I'll talk about the change method in just a bit. But for each of these queries, I just like have the two values, and then I essentially swap them just by calling change twice. So yeah, because like a swap is equivalent to two modifications. It's like an even more restricted version of that, but I don't use that restriction. For these changes, I handle the first element separately. I could have done this maybe a bit cleaner if instead I just made the array have a 0 in the beginning, but that's fine. And then I subtract out the deltas from something to the thing before it if it's positive, and something to the thing after it if it's like in the right direction, and then I add them back in at the end. So yeah, that's the idea behind that problem. Then one more problem that I solved, which was problem D. Oh yeah, the lamp one. Okay, so the idea behind this problem was as follows. We have a bunch of ranges, and we want to say how many groups of k ranges are there, such that, or how many groups of k ranges are there where all k of those ranges intersect at some particular point. So maybe we want to pick 2 ranges, so maybe in this case k equals 2. So we could pick these 2 here, we could pick these 2 here, or we could pick these 2 here. There are 3 ways of doing it. No, we could also pick these 2 here, so there are 4. Yeah. Okay, so how do we actually go about doing this? Well, here's the idea. We can do some n choose k stuff, but we have to be careful not to overcount, because like if we have a bunch of lines, right? Let's say we have some lines like this, and we do k equals 2. When this line ends here, let's say we do a sweep from left to right. When this bottom line ends, we can pick any 2 of these 3 lines. But the issue is, if we count picking these 2 lines, then later on we might also be able to pick these same 2 lines. Namely, when this line ends here, we'll also be able to pick these 2 lines. So in order to avoid overcounting, we're only going to pick groups of lines where this is the last time we can pick them. So if you give me some set of k lines that work, I can point to exactly the one and only place that I'll count it. In this case, if we want to pick these 2, the time this will be counted is the last time this is possible. That's going to be right here. So here's where I'll count these 2 lines. Before then, that won't be important to us, I guess. So here, if we want to count all of the, let's say we're at this x coordinate here, if we want to count all of the groups of k lines that intersect at some point, where the last time you can use them is right here. What I want to do is do some n choose k math, but we have to include this line in the group. So to do that, we'll like subtract out 1 from the n and subtract out 1 from the k, because we know we're forced to pick this line. Then we do like n minus 1 choose k minus 1 in this group. That's the idea. So yeah, so we do a sweep, like to summarize, we do a sweep from left to right. When some line ends, then we say, okay, we're going to count how many ways there are to pick a subset that includes this line. And we do that by saying, all right, at this endpoint, how many other lines are there? It's like that number of things, choose k minus 1. That's what we need to add. The math for that looks like this. So we're going to do a sweep. I have a bunch of events sorted by x coordinate. And I also store how many lines there are at this position. So then I go through each event. If this is a start event, then I add 1 to the number of lines that are at this position. If it's an end event, I subtract 1 from this line because it ends. And then I need to say how many ways are there to pick this number of lines, or to pick k minus 1 lines from this number that are currently available. And I only do that if there are enough to pick all of them. Yeah, so that's the idea. This is just fast exponentiation in order to do n choose k in log time, or in order to calculate like the inverse of some number in log time. I calculate all my factorials for n choose k in order 10 to the 6th beforehand. And then the, I guess, last thing to keep track of is for these events, you want to make events start before they end if both of those happen in the same position. So yeah, it's just like kind of an edge case to watch out for. And then for this last one, problem E, yeah, I don't have too much time to work on it today, but like you can do it in n to the 5th divided by some constant factor. I suspect they're looking for a faster solution. If not, these bounds are a little tight, I think. Maybe n equals 60 would be better. But, yeah, I'm not sure. I haven't actually implemented it, so I don't know how fast it runs. But yeah, the idea behind that solution would be you can do a DP where your state is like, okay, so first of all, the idea for how to count the answer is you have a bunch of zeros, and then you're going to like place some ones between them. So maybe you place ones in like these positions, for instance. Now you want to say how many pairs of zeros are there where like the 2 zeros have a 1 between them, basically. So yeah, the idea is when we have some 1, we can, like when we place this 1, we can add all of these like edges. We can get all of these points. So this just gives us basically, placing this one will give us 2 times everything to the right. So 2 times 5 here. Then when we place this one here, we get these 2 times 3. Hopefully, oh, okay, we get 2 times 3 here. Is OBS still alive? Good. All right, yeah, so that's the idea. So how do we count this? Well, one way we could do it is do a DP, where we store which position we're at in this zeros array. We store what 1 we're about to place, right? So like the index and the 1s. And then in order to count correctly, we need to store what was the last 1 that we placed. Like, where did we place the last 1? And finally, since we need the answer for everything, we also need the amount of like money we have left. So like the moves left. And then this DP will store the maximum answer. So that's one way of doing it. I don't know if this runs in time. That's a bit sketchy. This is the size of this DP will be the number of zeros. This will be the number of ones. This will be the number of zeros, like divided by 2, I guess, because it has to be smaller than this. And this will be n choose 2. But we can space save this by, we don't actually need this to be in memory. So this can be ordered 1 memory. So the memory usage will be small enough, probably. But the time complexity is cutting it close. It's about 2 times 10 to the 8th. The transition is order 1. You either place it or don't, so it's fast enough, I guess. But it'll be, I think it's probably close to the runtime limit. I'm not really sure. So yeah, I don't know if that's helpful. I guess you can check the editorial, see if their runtime is like end of the 5th divided by a constant. And if that's the case, then this should work. But if it's like an end of the 4th or something better, then maybe look at that solution instead of this one. So, all right, yeah, that's it for me. I thought the problems were good. Yeah, I guess maybe it was interesting, but if this was the intended solution, I think the bounds are too big. It'd be nice if I could see the runtime, like what people's runtimes were, to see if they were close or just like way under or something. That might give me a better hint for that. But yeah, anyway, thanks for the contest. I enjoyed it. And I hope if the round was rated for you, that your rating went up and you did well. And hope you enjoyed it as well. Thanks for watching and have a great day. Goodbye.